right, I think we'll go ahead and get started on our next Ivan Roundtable workshop, Suppress or Not to Suppress, Craft It.
Thanks for the Ivan committee and MR Resources at Q1 to inviting us and let us present our research and results. Hello, everybody. So this is a teamwork, not only teamwork at the foundation, but also team presentation, because we have 4 authors on this slideshow. But I'll be talking about the general background and some specifics. Then Krish will take over to present details for craft itself. Then Christina Metaxas and James Chen, the high school students from out of 5 high school students, will present their own so-called private project, because this general project, which I'm going to talk about myself, was the project for the whole team, but everybody picked another project for themselves for further analysis. So let me start. This is introduction of myself. This is my hometown in Hungary, which is more than 1,000 years old. Here are the co-workers who contributed to this project. Ken is my colleague and then sidekick all the time in the lab. Professor Sarah Ralston has always been our resource and collaborator for studies. And Dr. Meryl Simpson, who graduated from Rutgers in 2013, provided the data and so much of material which we discuss today. I mean, the original data on horses. So here is the 5+1 adventurers, Mateus, Christina, you'll see in person, James as well, Ken Conover, he's not a student, but is essential for the whole project and everyday activities in the lab, Ayelet, and then Joseph. So these 5 people down here, plus Ken and myself, work together on a daily basis and enjoyed each other's company. And I've been amazed how fast and how efficiently these people were proceeding with the project and understood every step in the process, including roadblocks in the software, which Krish helped out with, and big enthusiasm. So the craft, you know about it, complete reduction to Amplitude-Frequency Table software. And then we applied it for biomarker signal extraction from horse serum samples. I'll tell you in a second what we choose for extraction and for what reason. This is an approach which is a competitive alternative to a variety of sophisticated experimental methods, which I refer a little more in detail in a second, which aim to suppress the rest of the spectrum experimentally. They are abbreviated as DIRE and JEDI. There are great papers out there. You are welcome to take a look. I want to highlight that our approach is not a substitute for these suppression methods, rather an orthogonal alternative approach to find a quick analysis solution using only the water-suppressed one-dimensional spectrum, nothing else. And this kind of a spectrum is always the baseline when you start setting up experiments and analyzing any biofluid data for that matter. So again, our method is an alternative, an orthogonal method, gives a quick and easy access to certain selected targeted information. The suppression methods are still perfectly valid and highly competitive, also because there are some substructures in the suppressed spectrum which are meaningful, and at least at this point, our craft analysis cannot resolve that yet. So what is the disease which we identified or studied with these techniques? It is a long-term project for us with Professor Ralston, and this is OCD, osteochondrosis dissecans, which is a heritable cartilage disease of the horses. Poor horses cannot stand, and if they cannot stand at all, then they have to put sleep, unfortunately. It is also related to obesity and laminitis. And the problem is that there are things, subsets of the hoof of the horse, which separate from each other, and that's where the inflammation comes to the picture. This disease itself, I have to highlight also that it is a metabolic disease at the baseline. Again, has some heritable aspect. There are still details which are not fully clear, but again, as a side effect, so to speak, there is an inflammation process which takes place. And this is the review which we, with other students, formed during the summer programs 2-3 years ago. And this review is a fantastic summary of how certain lipoproteins NMR spectra are informative about inflammation conditions in the body. There is a GlycA and GlycB complex protein signals, which are all related to chain and methyls in lysine side chains, and that's why they are relatively sharp as of the rest of the spectrum, which could be very broad. And they survive suppression techniques as well because of their relatively sharp nature. And again, this is not a single material behind it. It is 4 or 5 proteins each, but they collapse into 2 signals which are characteristic. This review presents a couple of dozen of research projects in detail where the ratio of these integrals was followed, and then those identified inflammatory processes, which then covered the whole suite of disease conditions, cancer, and other inflammatory conditions. So this was the starting point, and we found that these signals are readily available in our spectra, and that was a very interesting note to make at the beginning. Here is a supporting information figure, which I extracted from Jeremy Nicholson and Julian Wiss and all the others in this big crowd at Perth, Australia. It is analytical chemistry in 22. And what is important that it lists the comparative presentation of spectra with different manipulations. Oops, sorry. So the first spectrum A is the full spectrum, only the upfield region. And then it shows that there are those signals of interest which we wanted to focus on. But it shows also that the spectrum otherwise is full of broad peaks, including all kinds of lipoproteins and metabolites in a cluster. The B is a conventional diffusion filter spectrum. CPMG is a commonplace application for diffusion filtering, which suppresses the broad signals and retains the sharper signals. However, everybody is suppressed at some level, and that's not under control. So there is a certain low-level modification of the relative integrals as well, which is a potential drawback. It is not too serious, but it is present. C is a DIRA filter. DIRA is diffusion and the relaxation filtering in combination. And that shows that the C spectrum shows that these peaks are very nicely separated. Most of the rest of the spectrum is suppressed, except some lipid or lipoprotein peaks, which are still present in relatively large quantity. And that's where the JEDI technique came to play. It is a J-edited, diffusion-edited combination, and it uses spin echo sequences to suppress these signals even further. And there are varieties of these. You can check it out in the original paper. The point is that there are still some broader signals which are unpleasant. And in the PGDE version, which I can't recall what is the abbreviation for, the suppression is almost complete for everything else but the selected signals of interest. Now, again, this is a very sophisticated, little bit complicated experimental process. I can tell you that when I asked Bruker to send me the pulse sequence, at least at that point, they said that it is proprietary because it is such an efficient thing to analyze spectra. just by a sophisticated experiment to extract information about disease conditions. But there is this idea that how about if we would extract these peaks using craft rather than going through these acrobatics and using only the original one-dimensional spectrum, which is the simplest possible, only water suppression applied. So this is a typical spectrum of horse blood. It is very similar to any mammalian blood sample, and many things can be identified just by looking. This is the small section which we are most interested in, the lipoprotein and acetyl groups, and choline composite signal here, which is abbreviated as SPC, introduced by the Nicholson group as well. And then here is the experimental detail. We had a cohort of 20 plus 20 horses. 20 was diseased and 20 was the control. And it was all done and presented by Mariel Simpson at that time, George Cook Scholar program thesis in 23. And that is an important side note I wanted to make, maybe multiple times, that this craft analysis doesn't need revisiting the sample. You can apply it to any data sitting on the disk, any old data, such as this, which was more than 10 years old. So the craft analysis can be done retrospectively, and that is a big advantage for mapping out information which is already collected earlier times. And here comes Krishnamurti, the magician of craft.
We invite you to get to know Q1. Q1 is dedicated to developing NMR systems from 400 to 600, as well as full system upgrades from 300 to 600 as well. You can get a lot of features in a 2-channel NMR spectrometer at a great price. So we invite you to get to know more. Contact us at q1americas.com or info@q1americas.com by email. Thank you.
Thanks, Ishwan. It's interesting that you put it as a magician, but my last slide said there is no magic. You will see that. In this particular, one of the challenges that I had today was talk less. That was my challenge. So I picked one item, one particular topic that is relevant to what this project that Ishwan alluded to, and then what we're going to hear from the other students, is resolution of peaks. And I want to talk about resolution in tabular domain. We know about time domain, we know about frequency domain. I'm going to talk about the tabular domain, which is a lot more easier to talk about as a phrase. So that's what I thought I will do. In order to understand what do I mean by tabular domain, I want to present to you the workflow that you have in any time domain analysis, in this case, graph. We take the FID, extract information to a list of models. And then this is where we actually apply our NMR rules. What is it that we want to analyze from this table? And then we generate a table that is NMR friendly in chemical shift, amplitude, width, and phase, whereas this is physics friendly, offset, amplitude, decay rate constant, phase, and so on. So this is where most of the focus is going to be. Majority of the time, we usually don't change anything in here. This extraction, this estimation happens as part of Bayesian process that we have, and that happens in an iterative fashion. But we want to understand the power or the limitations, either way, of this before we can start to apply these rules. These rules can be, because it's a table, these rules can be anything that you would normally do in a spreadsheet. Sort it, combine it, filter it, search it, group it, and so on, so forth. So, and then the visualization is step number 3, which is Spectra. That's Many times it's optional. Most your interpretation actually comes from the table after we apply our NMR rule. But visualization is an extremely critical step because we are visual animals. So we like to see what is done in this tabular domain. So many of these, almost all of the spectra that I will be showing is really not from time domain to frequency domain, but going through this sequence of events, unless otherwise specifically I say this is an FT spectrum, then that's a straight from time domain to frequency domain. So let's first understand what is time domain. This is NMR 101 for many of you, but I just like to keep reminding myself. At the same time, I'm proud of this particular slide because I spent a lot of hours trying to understand PowerPoint's animation routines that we have. So when in time domain, essentially we start with a pulse or a pulse sequence, and then I have examples of 3 magnetizations that we have vectors in the rotating frame of reference, and they all will have slightly different offset phase, for example, because there was some delay after the pulse sequence. So we call it T equals 0, but it's actually slightly a little bit delay. But what we are really measuring is the magnitude and direction of these vectors, no more and no less. So that in NMR language, that is amplitude, that is the magnitude of the vectors at time equals 0. Phase will be the direction of the vectors at time equals 0. Right? These are the only 2 properties that we actually measure in there. But except we don't do it right after the pulse and only 1 point, we actually measure over a period of time. So the magnetization processes, some of them process faster or decays faster, some of them process slower and decay slower, or process slower, whatever, any combination there are. So we have those 3 disappeared. By that time, we collected the data. What we collect is really detect amplitude and phase as a function of T. That's what FID is. Whereas, and it is now ready for the next pulse. From an NMR point of view, a signal is defined by 4 properties. It's not just about the amplitude meaning the magnitude of the vector, which is the quantitative NMR. That is fundamentally the quantitative NMR. And phase and direction of the vectors, that's the least, probably we focus on that very least. But there are 2 other parameters that in NMR we talk about. That is, one is the frequency, which is a chemical shift. That is nothing but a rate of change of phase with respect to time. And a decay rate constant or decay rate, I tend to use these 2 synonymously, but obviously they are two different parameters, definitions. But let's say constant, that's a rate of change of amplitude with respect to T. And these are orthogonal because the magnitude and direction are 2 orthogonal parameters that we detect. Decay rate and phase are the rate of change of one of those. So not necessarily anything to do with T equals 0, but to do with what happens during T. So this is where they become orthogonal. That's the power of power of NMR in time domain. Essentially, what we say that by this is we have each vector is represented in time domain is represented by an equation. It's exponential decay function because that's a rate of change of frequency phase. The other one is rate of change of amplitude, and that's what you see. And each one has every magnetization in the rate that we are detecting will have an equation. And this a sum of all these equations gives you the FID. In tabular domain, which what Kraft and Bayesian and all that does, is essentially representing these equations of these different magnetization that makes the FID in a tabular format. So you have the offset, you have the amplitude. Offset is the frequency, amplitude, decay rate constant, and phase. So this is the tabular domain, and we are going to take that tabular domain and do whatever we want to do and get frequency domain information. In fact, we don't even need to get a frequency domain. We can do all this sort and we apply NMR rules, user definable. This is where we can have some fun with it, how we define the rules. And we can get our answer that we are looking for. And so the frequency domain is nothing more than visualization of time or tabular domain. No more than, no less. We We don't access the frequency domain to extract any information. It's only a validation at the very end of that. That's the tabular domain, definition of tabular domain. What can we do in this part of the workflow? I'm not going to talk about the Bayesian aspect of it, but I'm going to talk about the post-Bayesian aspect of it. What can you do? But we also need to worry about, I start talking about resolution at the beginning. So if we talk about resolution, we all know what resolution means, or we think we all know what resolution means. But if you go to the literature, there's a definition galore. Resolution, some people talk about how I can separate one signal from the other. Some people talk about resolution as how well how sharp the peak is, which is a line shape, but we have the definition. I'm not questioning which one is right or which one is wrong. There are a lot of definition. From our perspective, what we want to talk about resolution means how do I resolve these rows in tabular domain? How well can I resolve the rows in tabular domain? If I can resolve the rows in tabular domain, I can do more sorting, combining, filtering, anything that I can do with Excel spreadsheet. I can do with that. So we need to understand what is the resolution in tabular domain. For that, we need to understand the limitation and the power of the previous step, which is the Bayesian step. And that's what I'm going to talk about in the next couple of slides. So in this particular example, I took an example. Some of you probably have seen this, but I took an example where I said, I'm looking for a doublet. I'm going to resolve a doublet. It's very simplistic approach. Resolve a doublet, and here is your acquisition parameters and how we process it in time domain to frequency domain, FT process. Except that these two doublets have a line width of 0.2 hertz or 0.5 hertz, 1 hertz line width. Each one of them is a 1 hertz line width. Each one of them is a 2 hertz line width, and so on and so forth. So this is what you would get if your J coupling is half a hertz. You can try to resolve these guys. You can probably just get a bare resolution because your line width is about the same as a J. Whereas once you go here, you don't resolve. Even if you try as much as most potent apportization, squared, sine, Bell, window function before Fourier transform, you can probably make this resolvable. That is, you can probably pick that doublet. These two are completely hopeless, right? Now let's take a look at how Bayesian is capable of doing this. This is a doublet with the J equals half a hertz, and the first step is line width of 0.2. These are all simulated with noise thrown in just to mimic a typical quantitative NMR. So the FT was we generated as FID, and then we applied that to Kraft or Bayesian, and then looked at the model that comes out of it, and then we resynthesize a FID and then Fourier transform just for our visualization purpose. So you can see this truncation artifacts and so on, everything that is part of our frequency domain analysis. So that's AFT, Kraft. This is a piece of cake because the resonances that we are trying to resolve is much well separated compared to the line width of the individual component. When you go to the next one, which is about the same as the individual component, the line width being, you can still resolve. You can still resolve it even in frequency domain, meaning FT. You can resolve that. Now I'm going to the next one, which is 1 hertz line width, half a hertz J coupling. And you can resolve that. You can watch this as a frequency. I mimicked it on a 500 megahertz amplitude decay line width instead of a decay rate and phase. And that's twice as much. The line width is twice as much as the J coupling itself. This one is 4 times as much. And this is 8 times J coupling itself. And you can still see the resolution power because the tabular domain, the Bayesian says that I can fit this FID only by the best fit that I can get is by fitting it to 2 exponential decay function, each one having a 4 hertz line width, frequency, separation, and amplitude. Here is an interesting thing that I did at that time. Instead of instead of doing 3.64 second acquisition time, what happens if I cut that out by 1/4? So this is actually less than a second acquisition. So you don't have enough points to see the entire decay. And the line width is 4 hertz each, half a hertz separation, doesn't blink an eye. I can take it down to 0.6, doesn't blink an eye. So I'm not trying, I just want to make sure that I'm not cheating in the sense, if you cut it down furthermore, you lose it. Meaning that it doesn't have enough information, enough data point to resolve that differences in the two frequencies because of the line width that is masking. So this is a very common approach we see. The more points you supply, the better it can do. For example, one of the things that we tested in a real world is quercetin, where we took one of the J coupling. I don't think I have a structure here. I thought I had a structure. But what I did was I added a width to the FID myself. So these are 0.5 hertz with additional line width, 1 hertz additional line width, and so on and so forth. And the J was measured from Kraft using that. These are examples of how the Kraft estimation happened. The coupling constant is about 2.2 hertz and 2.2, 2.3 hertz. And it doesn't matter if the line is wider, as long as you have enough signal to noise, enough points to supply, you can separate those. This is the most interesting one. This is real. That's a synthetically added line width. Whereas here, this is a strychnine, 2-second acquisition, classic 500 megahertz proton spectrum. And I'm just example-wise, I'm showing you about 4 different multiplier patterns here. That is, even by visually, is trivial. That's a triplet, doublet of a triplet. This is visually trivial. That's a doublet of a doublet AB spin system between these two. And this one is obvious. You can see that from a structure, you can see that is broad. That's a quartet, actually. It's a quartet, and that's a doublet. So what made me think about it was, there's another splitting here. These two signals are split by 2. And let's look at what is the characteristic of that splitting. I haven't seen that kind of a splitting before. Let's watch this one. So this is I took it as my control, which is the same data from a different proton. That's the line width of the half height, not measured in a frequency domain, but measured from the decay rate constant is 1.37 hertz plus minus 0.02 computational error, right? Whereas this guy is 0.148, very similar, about 10th of a hertz difference in line width, and measured error is less than 0.11 hertz. Whereas the J couplings are 10.5, which is a major coupling, and there is a minor coupling, which is 0.5 or 0.6, almost to the same level, and much less than 1/3 of the line width of the individual component, isn't there? This is 4 different line widths put together, average. This plus minus comes from what is the standard deviation from these 4 only, nothing else. And frequency error is still, that's not in ppm scale. That's actually in 100. It's about 100th hertz frequency error. This frequency error is not measured as against somebody. It's a frequency error in the measurement itself, in the computation itself. So we are very high accuracy. We are saying that very small coupling constants that we missed it because this was 1.48 line width. This is 1.38 line width. I still yet to see somebody willing to do an experiment, come up with an experiment to measure that. I would like to see that. Now I'm taking the other way approach. In the previous one, I simply changed my line width, or I tried to measure if I have a splitting if the line width is wider than the J splitting. Here I'm going to do the opposite, meaning that here is an example where I take 3 lines 10 hertz apart. You can actually see the noise, so meaning that this is synthetic, but I synthetically added noise as well. They are separated by 10 hertz from each other. 1 hertz line width, 2 hertz line width, 3 hertz line width. You can see that. What then I'm going to do is another example where they are separated by 1 hertz from each other. One is a 10 hertz line width, the other one is a 1 hertz line width. So that's what you see there. Fourier. I'm going to compare that to isogamous. Two signals that are exactly the same frequency. These are synthetic, so these are exactly the same frequency. 1:1 ratio, 1 hertz and a 10 hertz. I want to take it further. I want to do 1 hertz, 10, but in a ratio of 10:1. This is pretty much 1 hertz signal with a very small amount of 10 hertz signal, because that's 1/10 of that. And then I'm going to compare it the other way. And the last comparison is going to be two signals that are 0.2 of a hertz in line with difference, but isogamous, exactly the same frequency. Can we separate that? These are the kind of problems that we face when you are dealing with when you are dealing with background protein signals. One is broad, the other one is narrow. How low can we push? That's the question. So here is a crafted 2D spectrum of the easiest example, which is the 3 well-separated piece of cake. One of the things that I'm going to introduce is I'm going to introduce a spectrum which is not conventional chemical strip spectrum, rather the crafted T2 spectrum. Right? This is nothing but taking this line width and convert that into T2 and plotting the T2 in millisecond against amplitude. Right? So you have 3 T2s. The resolution here is phenomenal because the three signals differ in a very good line width. So the resolution of this is pretty straightforward, because now the width is a third column or one of the columns and has nothing to do with the frequency column. Yeah, those are orthogonal in tabular domain. So I took the next one. I'm not going to show you all of them very quickly. The 1:10, 1 hertz and 10 hertz, slightly offset from each other. Again, a piece of cake. You can see the two models that it picks up. You can take that same one, put on top of each other, meaning that this is an isogamous signals, and you can still separate them. You can separate in the table, that's 2 different rows in the table, in tabular domain. If you take a 0 to ratio of 10:1, meaning that I am biasing the dynamic range against one in favor of one than the other, you can still separate them. You do the 1:10, you can still separate them. Now here is an interesting one. That's the 1:1.2 line width ratio, isogamous, and you can still separate them. Because in the T2 spectrum, they are well separated, meaning that it is very easy to find the differences in the decay rate constant between the two. Here is another one that I did. This is the other example, 1:2 example, isogamous. Watch the acquisition time. That's 1.82 second, 0.4445 second. This is less than half a second of acquisition. And that's your Fourier transform, Kraft results, and that's your models that are in there. You can separate them. Obviously, just to make sure that there is no free lunch. If you don't give enough data point, it's going to come back with an average result, meaning that it doesn't have enough information to separate the two. So it's not just to make sure that we are not just throwing in only the successful results. Yes, there are limits to that. How do we apply? Here is an example of this, very similar to what you're going to see. I'm almost done with my talk. Here is an example. This is an mRNA spectrum. This is an mRNA spectrum. FT result, that's a Kraft result, that's a residual. The best that you could probably do with this, right? What can I do with this? So if you have a resolution, as I talked about in the previous two sets of slides, one is the frequency separations versus line width separation. What can I do with this? How can I exploit that in analyzing a spectrum like this? Here is a way I can do that, meaning that I can say take all the models, all the rows that are in my table, and take away filter only those models that has a very narrow line, meaning less than 10 hertz line width. And that's the spectrum of that. That's a narrow model spectrum. This is an intermediate size model spectrum. Potentially, you can correlate this to correlation coefficients and things like that, and then say these are all small molecules. Looks like small molecules to me, and these are medium-sized proteins. And then the rest of them that are 40 hertz or wider is the background large protein that is coming in. This comes from not from some filtering experiment or pulse sequence or anything. All it did was we took that into a table and then we simply applied some NMR rules. We applied an NMR rule of 10 hertz or less. I'm going to call it small molecules. Show me that spectrum. Between 10 hertz and 40 hertz, I'm going to call that medium-sized proteins. Show me that spectrum. So I'm applying some NMR rules. And that NMR rule is what gives me the spectrum. In fact, it is the opposite, that what I did was I didn't set the entire thing. I just took all the rows and then I can just plot each one of them. So there are this many rows with medium-sized signal, this many rows with sharp signals. So this is it. This is a benefit that you have in tabular domain. I just want to remind you, all of this came not from an experiment, but from a proton spectrum. Essentially, because I went into a tabular domain, used the power of Bayesian that is there, and this is the real sample. That's a typical noise that you see. That's a typical spectrum that you see of mRNA. That's a tabular domain. I can rip it into molecules of different sizes, perhaps. You can play with it whichever way you want. That's users' NMR rules. It's like how I will analyze a 2D spectrum, for example. Talking about 2D spectrum, what I'm going to take a trick is to plot the width or the T2 star against the chemical shift. Because I have a T2 star is my decay rate constant column, and my chemical shift is my frequency column. I can plot, this is not a 2D plot in our way, contour plots. This is just an Excel spreadsheet scatter plot. And you can see the T2 star, all the T2 stars that are very short T2 stars are all blue colored, and the pink T2 star, I put a line here that is the equivalent to a 10 hertz line with T2 star 1 over pi 10. So that's, you can play with that. There is an even more interesting way we can probably visualize this. This is spectral visualization. This is table visualization. Instead of T2 star again ppm, to me this is annoying because it is pretty much a logarithmic scale. Why not plot line width against frequency? Here is a 2D spectrum that is available from the tabular domain of a 1D acquisition. Why not use that to do whatever else we want to do? So it is available, it is there, it is hiding from us. And we are essentially taking that 1D spectrum, putting it in tabular domain, and then plotting it in a 2D. I could not do more than a spreadsheet because this is literally last night at 6, 7 o'clock I came up with this. Maybe we should plot this way. That's an Excel spreadsheet. Yes, I do have some work to do to actually plot it in a regular 2D fashion, meaning the contours represent the amplitude of these signals. So now we have a new 2D spectrum representation out of a 1D input. That's a 1D input. And the last, I'm going to stop with this, is we talk about broad peaks I talked about with the mRNA example, and you're going to hear from Christina and James on a little bit more complex systems as well. We are all talking about broad peaks. Broad peak can also be baseline. Yeah. Here is a fluorine-19 spectrum. That's the fluorine-19 chemical shift spread. That's your fluorine-19 background signal. This is your digital filter issues, whatever you want to call it. There is a problem with this. So what do we do about it? Number one, we either go back to the probe group or probe Toby or some Brooker probe engineers and say, I want a fluorine-free probe. Make me one. And spend dollars on this. Let's take a look at this in what is baseline or broad peaks. Broad peaks and baseline are the same. This is a slide stolen from Frank Delaglio. Baseline is nothing more than distortions localized in the early point of the time domain. And that's what causes all this baseline problem. So that means this is his, when he gave a lecture on behalf of Kraft, he said, but you can model, can still be accurately fit to the remainder of the data. You can ignore these guys and do the remainder of the data. So I started asking, say, why not even bother with it? Just discard the whole thing. Don't collect the data or throw away the first several points. What happens to that? For example, if I throw away the first 50 points on this FID, just left shift the FID by 50 points, I get a beautiful baseline because all these guys already decayed off. But the price I pay is 18,000 degrees of linear phase error. That's 18,000 degrees. So this point here and that point here differ in 18,000 degrees. That's a pain. That's a pain. Now, what is that? Where is that linear phase error coming from? Let's go back and look at your time domain. So here, this is what we saw, pulse. After some delay, there is this vectors are sitting there. I'm going to, instead of collecting the data at time equals 0, I'm going to wait. 50 dwell time, I just waited. They're all pointing all over the place. And so what? It's an equation. This doesn't have to be as 0. That's an equation. That can be as 50. So if I know the amplitude at 50th dwell point, just like you can calculate amplitude for any of the subsequent dwell points, you can also calculate everything from the previous 50 points. Essentially, it's a linear prediction, but not linear prediction in the conventional way, but linear prediction of an individual models. Just your magnetization back 50 dwell points to 0. And you can do that mathematically with click of a button. So if I do that, okay, so my amplitude is amplitude of T50, and then I can correct for that, and so on. And then now I can simulate my experimental, my Kraft spectrum, all in beautiful, in phase, no baseline issue, none of these issues. Whether it is a baseline issue in your integration, all that thing, or baseline issue that gives you dynamic range problem. For example, this is F19 background. That's a real peak. These two are real peaks. And the second thing that you will notice is this spectrum is much smaller than that spectrum. It's not smaller. It's the same spectrum. It's just sharper. It's sharper, so it shows up taller. Why is it sharper? The experimental data came from 30 millisecond acquisition. This is a steady state free precision data. It is collected only 30 millisecond per scan. But once you get into your tabular domain, there's nothing that is telling me in the tabular domain I need to resynthesize to 30 millisecond. There is nothing, no information here which says that that I am limited to 30 millisecond. So I can start with the time domain data, which is 30 millisecond, go to tabular domain, I can resynthesize my time domain, this time just synthesize it for 1.5 seconds. And then I can do a Fourier transform, I get the spectrum. So essentially, we are giving a narrower signal because it is decaying slower. You can see the decay rate constants are slower. Yes, you will get a narrower spectrum. This is the principle we have published 10 years ago on 2Ds. And that's the same thing applies even in here. So once we have the magnetization, once we have described our NMR in tabular domain, there's a lot more we can do that we couldn't do in basic time domain or in frequency domain. And it is there. We just couldn't do it very easily. In tabular domain, there's a lot of benefit doing that. With that, I'm going to stop. So essentially, as I said before to Ishwan, there are no miracles. We are really looking at what is in the NMR data. What is, but there is no substitute for better signal to noise. Better the raw signal to noise, the better you will fit, because this data analysis is a comparison of a model to the data. The more point one supply, the better would be estimations. We saw that before. In the truncated acquisition time, I couldn't resolve what I could resolve if I have a longer acquisition time. But the interesting thing is this doesn't have to be longer acquisition. We just need more data point. What that means is oversample the data. You can have a same 2.2 second acquisition, but oversample the data. Have more data points. It's free, because your analog signal is coming in continuously. You digitize it faster. In fact, we digitize it faster. We just go back and throw them all away by downsampling to the spectral width. That information exists. That information is pretty good. We have lots of examples where the more point can simply be by oversampling the data, not generating large acquisition time. Because at the front end of the FID, you have more signal to noise than the later part of the FID. So with that, I will stop, and then we will continue the workshop. Thanks.
As always, give a word for our sponsors. First, MR Resources. They've been around for 39 years at this point, servicing the international NMR community and doing pretty much anything and everything that needs to be done with your NMR system. Magnet quench recovery, magnet and system moving and relocation, service contracts, reconditioned NMR systems, reconditioned magnets. And it's always very important for me to point out that they have absolutely a full supply of spare parts for everything that they sell. And they have engineering expertise that I dare say is second to none. Give some thought to doing business with MR Resources.
So, Chris, don't tell me you are not a magician. You are. And you are doing so well. This oversampling business really grabbed my attention. And it is a fantastic additional little trick. But let me then continue the story on our side. So this is the spectrum we start with. This is the full spectrum. Again, nothing but the water suppression. Everything else is there with full intensity. And these are the signals we are interested in: GlycA, GlycB, and the SPC signal. This is beta glucose. These are lipid peaks, and there are all kinds of other mixed peaks: lipoproteins, small metabolites, and everything. So what we are planning to do and want to do is extracting the integrals of these selected signals only, nothing else, because they have characteristic message about inflammation in the creature. And the ratio of these integrals will be the message which we wanted to extract. And this is an example which mimics or follows which Krish already shown, but this is the full spectrum. This is the spectrum with the model subtracted, so you don't see the signals of our interest. This is the full model, and the acetate peak is also added just for control. And these are the individual components, including the acetate. But the important thing is that now we have the independent integrals for the selected peaks and nothing else in a tabulated format. This is a conversion to frequency for visualization, but that's for our animals, ourselves as animals of visual nature, as Krish already pointed it out. Then here is what we ended up with, and this is the fantastic confirmation of what we can do with these selected integrals. In fact, this scores plot in a multivariate analysis using SIMCA, an OPLSDA analysis compares the GlycB SPC ratio and converts it to a scores plot. The OCD diseased cohort and the control cohort are very nicely separated. So nicely that if we take the validation plot of this spectrum, it is very, very good. And this is again the GlycB SPC, which is often used in the literature to identify the inflammation conditions. But here are the other options, because we can take the GlycA, GlycB ratio, which comes from the review. Originally, the SPC was not considered in that review. It was introduced by the Nicholson group. But GlycA, GlycB is not too bad, not as good as the GlycB SPC combination. Here is the GlycA SPC. Now that's far from satisfactory, to say the least. And here is a multivariate scores plot, OPLSDA. When we add up the GlycA, GlycB, and then measure it against the integral of the SPC. Now, this is not too bad, and so often it is also used in the literature, especially Nicholson's group introduced very, very sophisticated methods to do this suppression and then analysis using as low as 80 megahertz NMR spectroscopy. And I would certainly recommend you to look it up, and I'll be happy to pass you information if you are interested. So here is a summary of our project on this set of 20+20 horses. The first important message is that CRAFT is viable and highly simplified tool. So the concept is valid that we can extract important biomarkers, take their integrals, and then result or lead to important distinction and diagnostic result. It is all these signals can be quantitatively extracted. It also shows that OCD has inflammatory component. Again, OCD is a metabolic disease, but it has an inflammatory condition associated with it, and that's what we can map out here. The message I mentioned already before, that CRAFT can be used retrospectively on any earlier data, which is good enough quality, of course, but other than that, just a simple one-dimensional voltage-suppressed experiment. And then we extend this we are in the process, extended it for additional data sets, such as Mustangs against domestic horses. James will tell us exotic results of Falcon data, and so on and so forth. So this is my conclusion. Thank you very much. And then here is the show for Christina and James, one after each.
Hello, everyone. I'm Christina Metaxas, and I'll be talking about CRAFT and its ability to analyze inflammatory biomarkers in complete horse serum 1D NMR spectra in relation to laminitis. I worked with Dr. Pelkzer over the summer, a part of the Princeton Learning Laboratory program, to analyze the OCD data he just presented. And when we were done analyzing the data, Dr. Pelkzer gave me my own set of data to analyze, which involved horses with laminitis. The horse serum samples were ethically collected by veterinarian Dr. Ralston and Dr. Simpson at Rutgers University and analyzed by Dr. Pelkzer at the Princeton University NMR facility. So, what is laminitis? Laminitis is the inflammation ensuing separation of the laminy tissue from the coffin bone. This is the second leading cause of equine death. Laminitis is caused by a high-grain diet most of the time. Horses have no enzyme to digest the sugar fructan, and it passes undigested into the hindgut. With excessive grain consumption, undigested carbohydrates overflow into the hindgut and kills the gut bacteria due to the change in pH levels. The death of these gut bacteria lead to the release of endotoxins that are absorbed into the bloodstream. Endotoxins can compromise blood flow to the peripheral circulatory system, which includes the hooves of the horses, and altered blood flow to the hooves can trigger laminitis. Endotoxins also trigger an immune response, which causes inflammation. The immune response often results in the release of acute phase proteins, many of which are glycoproteins. Endotoxins also affect the levels of SPC in the body. And some symptoms of laminitis include soreness and pain, hot hoof, which means the hoof is hot to the touch, and lameness, which means that the horse can't walk properly. 50% of US horse operations reported having at least one horse with lameness. So this is a very widely affected disease for all horses. And as laminitis is often caused by obesity, high grain diets, the inability to metabolize carbohydrates in horses, it's no surprise that there has been a strong correlation between abnormal glucose and insulin metabolism in the presence of laminitis. For this reason, we investigated specific bioinflammatory markers associated with abnormal glucose and insulin metabolism. In this case, the bioinflammatory markers were glycoprotein A, glycoprotein B, and SPC. So clearly we used NMR to analyze these bioinflammatory markers. We ran the samples on 500 megahertz NMR machines. And as everyone I'm sure has heard already, instead of using the traditional, more time-consuming NMR analysis methods, we employed Craft. Craft works in the time domain as opposed to the frequency domain. And Craft is superior to the traditional frequency domain analysis as it entirely eliminates the need for baseline and phase correction. It also has an improved capability in calculating amplitudes of overlapping signals, making it significantly more reliable and accurate. In figure 3 and 4 show the interface of Craft. Once you have your spectras from your NMR, you can download them onto your computer, upload them into Craft, and then choose whatever spectra you want to look at. Once you've uploaded them into the program, users can highlight the regions of interest based off established peak values of specific bioinflammatory markers. Those are the regions highlighted in yellow. One of the most valuable aspects of Craft is its ability to analyze many sets of data simultaneously. And additionally, once these spectrums have been analyzed, they're outputted as spreadsheet values that can be directly inputted into programs such as Excel and into other analysis programs like SIMCA, which I use to analyze all the data. This allows for really easy group collaboration, and I know it really aided our ability to do group work over the summer. Specifically for this case study, I used a 22+22 cohort sample of healthy and laminitis diagnosed horses. And most importantly, Craft can be retroactively applied on many data sets that have already been acquired, as the standard water suppressed full spectrums are part of the acquisition packages, which allowed me to be able to analyze all this data. Figure 5 shows the full spectrum routine protocol with only water suppression. I know Dr. Pelkzer has already explained a little bit of why we used the water suppression, but there's significant overlap of all three signals of interest with other peaks. This overlap can be removed with experimental suppression of unwanted signals. This approach, however, affects all signals on some level. For this reason, we use the full 1D spectrum with only water suppression applied present in figure 5, which ensures that all resonances will be present with undisturbed intensity. Figure 6 and 7 on the next slide show how much the peaks are affected when various filters are applied to the spectrums. And you can see the difference in the peaks with all the different filters added. From here, I use SIMCA multivariate analysis to create OPLSDA score plots for the full spectrum using the SPC-GlycB ratios. As seen in figure 8A, the clustering is pretty clean, showcasing the true extent of the validation. Monte Carlo cross-validation was done to test the validity of the statistical model using R² and Q² values, R² representing the goodness of fit and Q² representing predictability. And all of that is shown in figure 8B, which shows the validation of the OPLSDA score plot of SPC in the GlycB ratio. For all the other ratios, GlycA, GlycB, SPC, GlycA, and SPC, GlycA plus B, they were all statistically significant, and the Monte Carlo cross-validation validates that, but they did not produce satisfactory responses of correlation validation compared to the SPC, GlycB ratio. So pretty similar to what we found with OCD. A separate but special case I wanted to talk about was the horse Dandy. Dandy's blood had so many lipids in it that when it was first drawn, it was yellow. This immense amount of lipids was shown in his spectrum as the overlap almost hid some of the bioinflammatory signals completely. Previously, Dandy had to be excluded as his values were not distinguishable by previous NMR analysis techniques. Kraft was able to separate the bioinflammatory peaks. This spectrum shows how easily and accurately Kraft was able to distinguish the three peaks, and you can see them right there. In conclusion, Kraft is a simple but competitive alternative approach to the variety of sophisticated experimental methods which aim to suppress the rest of the spectrum and keep only the peaks of interest. Kraft selective extraction uses full information content of the spectrum without any modifications or loss of sensitivity. This study proved that Kraft is a viable and deeply simplified tool for diagnostics. This research focused on three major bioinflammatory markers: glycoprotein A, glycoprotein B, and SBC, but the concept is valid to all identifiable bioinflammatory markers. This study also proves that, in fact, laminitis is an inflammatory condition. The ratio of SBC and GlycB was shown to be clearly separated from healthy and diseased cohorts when multivariate analysis was applied, as shown in figure 8a. And Kraft can be applied retrospectively, which is super important, which is how we were all able to analyze all of this. So that's one of the reasons that Kraft is very helpful and useful. And in the future, we aim to apply Kraft to other organisms and humans for various diseases. One particular disease of interest is metabolic syndrome, as its symptoms include an increase in specific bioinflammatory markers that have already been identified. It also closely is linked to laminitis, as metabolic syndrome is the inability to metabolize carbohydrates and can also cause laminitis. Thank you.
I guess I'll present. My project focused on the identification and utilization of biomarkers in falcons with aspergillosis, and I decided to use Kraft technology since I kind of wanted to prove that it was a much easier alternative to the traditional methods. And before I begin, I want to thank Istvan and Ken for their support on my project, as well as Krish for his advice on using the Kraft technology, and also to Dr. Lucia Papalardo for the original collection of the Falcon data. So a bit of background on what aspergillosis is. It's a pretty widespread respiratory disease caused by a fungus called Aspergillus, and it affects the lungs of an organism, and it's very common in both birds and mammals, including humans. Actually, this data set came from falcons that had aspergillosis in the UAE, where falconry is like a big cultural thing, and there's like a lot of falcon shows that are happening in the UAE. So for humans, aspergillosis is particularly deadly towards immunocompromised individuals. And so the project aims to kind of see if there can be an early detection or like a way to detect aspergillosis using NMR, since it is an extremely deadly disease with a incredibly high mortality rate if not detected early. And so the goal is to see if certain metabolite components can vary specifically with the disease. And so a little bit about the data. So Dr. Istvan Pelzer provided me with the data set, but it was originally collected by Lucia Papalardo, and it originally came from a Falcon hospital in Dubai. And so for this project, I decided to not use the relaxation filter spectra and only use the water suppressed spectra, so that we can have like a more complete view and include like the smaller peaks in the data. And so I did do some processing of the NMR spectra using traditional methods, like using MNOVA. And this was mainly to serve as a sort of guiding reference for the project. And also, I wanted to create something called a back calculated coefficient plot to help kind of identify systemic variations between like disease conditions and certain peaks. And I would like to make note that the spectra of falcon blood is pretty distinct from that of horses, and that makes it a in my opinion, a very unique and interesting project just due to like how important falcons are as a cultural tradition in the Middle East. So here is the back calculated coefficient plot that I was able to generate. So how did I like create this? Well, first I superimposed all of the spectra in MNOVA, and then I exported it as a CSV file into Simca, and basically Simca gave me like some key statistical metrics like the loadings, weights, ppm, and standard deviation for each peak, and I was able to import those metrics into MATLAB, and I ran a script on these metrics provided by Pablo A. Hogenberg, who I believe was actually at Princeton University for some time. And so here's my back calculated coefficient plot. So the more, I guess, red it is, the more like significance that these peaks hold. And so if the peaks are higher or like positive, it indicates that that peak is the integral of that peak is higher in the sick cohorts. And then if the peak is down below here and negative, it indicates that there is lower values of that peak in the sick cohort. And so I labeled some like pretty important peaks. So the ones I used were the three OH boot peaks, like this one and this one, as you can see here, as well as GlycA and SPC, as you can see labeled here. I also did some labeling for the other peaks that were of interest. And so now is the phase where I began to use craft analysis. So here's a screenshot from the craft interface. As you can see, so on the left side is like the parameters that you want to set for the craft analysis. And then here's just an example of some highlighted peaks that I decided to analyze. So in this case, these three were the three OH boot peaks. And what you basically do is you just highlight like a range that you want analyzed, like which is shown in this green box, and you send it into the craft, and it outputs like an integral value, and it's extremely easy. There's pretty much no like graph processing needed, spectra processing needed. And actually you can superimpose. I'm pretty sure it's like basically an infinite number of spectra, and you can analyze those at the same time, which I thought was extremely helpful. And also you can have like a preset. So you can highlight like which peaks you want to analyze beforehand, and then you can save that as a file. And so for every like Spectra onwards, you can just load that file in and it would automatically highlight the peaks that you want to analyze. And so I thought that was also extremely helpful as well. And so some of the key biomarkers that I included in my study was SPC, the three OH boot peaks, as well as GlycA. So after I got my craft values, I ran multivariate statistical analysis in Simca. So this graph you see here is an OPLSDA scores plot. And as you can see here, there's really good separation between the healthy and sick cohorts. And so the ratios I used for this specific analysis was SPC over GlycA, SPC over 3OH boot 1, and SPC over 3OH boot 2. And the data was also validated by a summary of fit metric, as well as a Monte Carlo cross validation. And so as you can see here, the summary of fit yielded very good results. I think generally for values above 0.5 would be very good validation. And as you can see here, it's pretty good validation. And so for the Monte Carlo cross validation, it also showed very good results. As you can see here, there's like a pretty steep positive slope, which indicates that the data is statistically significant, and the model works very well for predicting whether a falcon is sick or healthy. And so, in conclusion, the study found that SBC, GlycA, and 3-OH boot were able to provide very good separation between sick and healthy cohorts, and also that craft-based metabolomics and statistical analysis improves disease detection just because of like how easy it is to analyze like a large amount of spectra in craft, especially when you can basically just take the integrals of all the peaks in a spectra and you could do that in like a minute. It's very, very quick. I believe like 34 spectra took me like I think under 20 minutes. So the whole thing like craft is just very, very quick in getting the integrals of the NMR spectra. And so the conclusion is that like these biomarker ratios like GlycA, SBC over GlycA, SBC over 3-OH boot can very well be applied to disease detection of aspergillosis in the future. And I think it shows very good promise for, I guess, like the future of NMR, especially since like there's like the development of the benchtop NMR, which is definitely small enough to be put in a clinical setting. And I think combined with like craft analysis, it can make like NMR into a clinical setting like a really tangible reality.
Congratulations to both of you. It was fantastic and very nicely done. Thank you so much. So the next phase is potential for asking questions or comments or whatever the audience is interested to contribute with.
I want to congratulate other three who didn't present today, the
That's
team
correct.
members. I think all of them did a fantastic job of
And
this.
I should also point out that they've been working in a real team. So they sit around that round table, not only for the photo, but all day long, and then exchanged ideas and then presented results and corrected each other in real time. So that was truly a teamwork all over the time.
Very good. I think the workshop is open for discussion. Anyone has any questions? I just wanted to bring up one definition, if I may. We do talk a lot. I mean, even today we talk. I do too, about integral. I think sometimes our old habits die hard. Integral, by the very definition, all NMR signals are asymptotic. Yeah, they are Lorentzian line shape. Integral by definition is we approximate plus minus some frequency in the spectrum and at data points in there. So integral by definition, the way we do integral is by definition is approximation. It may be 99.999%, but it's still an approximation. Whereas amplitude is the top of the sinusoidal function. So amplitude is the true integral. It is equivalent to if you have only one signal in your spectrum and you have the ability to integrate from plus minus infinity. That's amplitude. So craft doesn't give you integral. Craft is a time domain, so it is essentially gives you the sinusoidal functions, and the top of the sinusoidal function, which is time equals 0, is because they are exponentially decaying sinusoids, is amplitude. And so one day we will not ask about craft integral, rather craft amplitude.
Yes, I agree. We should be very careful with the precise terminology.
Yeah.
This time equals 0 amplitude is the real.
Exactly. That's the magnetization we are trying to. That's
what the real spectra cannot do, because time 0 doesn't exist in real NMR spectra. I mean, as a collected information.
Yeah.
So whoever wants to ask question or make a comment, just unmute yourself and then please contribute.
I have a question. My name is Jacob Yoder. I'm a NMR scientist at Los Alamos National Lab. I was trying to figure out, how do I get Kraft to try it out?
Oh, no, it is, we can talk about it, definitely. It is, Kraft as a technique is published. So the methodology is in the public domain. There are several papers in the last 10 years, including a review in 2 years ago. But Kraft as a tool, as a software, is at this point is currently available only from us, meaning us includes me and Dan Iverson, who is also in the audience today. That is a commercial product. So we can talk about how to deploy something for you offline.
And I suppose the good interface is also an important issue, because
True. Yeah.
for users who try to apply it, it is a major help.
Yeah, that's another thing that I was going to ask Christina and James as users who came unbiased with prior NMR interfaces. How difficult did you find? What would you have preferred to be different, if there is any? Feel free to. I have my shield up, so
Don't give mercy.
no mercy.
James, do you want to? I
Yeah,
think
yeah.
what we most needed was an undo button, like a back button, because at some point in time we may have deleted some things that we very much needed or accidentally did things and there was no way to reverse that, so we had to start all over again, which was
Okay.
sometimes a little frustrating.
Yeah, another thing I would like to add is also that Craft takes up like a decent amount of space on your computer. And I had like my computer wasn't very good. And so I only had like 20 gigabytes or so in my computer before I downloaded Craft. And so at some point I started running out of storage. But I think like if you have a large enough like computer storage, I think you'll be fine.
Yeah. Yeah, undo button is always a very useful request. It I'm sure Dan Iverson is listening, so I will leave it figure out how to go back in time in the way commands are executed. So,
But that would
but
increase the storage requirements, because you need to store the intermediate results step by step to certain number of cycles.
another thing, James, to answer James' question, it can certainly be much less space. That is primarily the problem that the way I built, in the sense that I'm more of a researcher than a product developer. So I sort of, every step of the way I want to go back in time, like Christina asked. So I keep, instead of going back in time, I keep it every step of the way, I save it. And that's another place for improvement from a user interface point of view. Because Ishwan, one thing that came out to me today from what Christina and James talked about is how easy it is. So when you are saying how easy it is, I look at it as perhaps we have to go interfaceless. It should be a command. You provide a protocol, you build a protocol, you execute a command. It should happen. There should be no reason for, well, there can be a reason for interface to build your protocol, no reason for interface to run your protocol. That's the take home message that I'm hearing.
Good.
Yeah. Anybody else? Questions?
Yeah, I had one question about
Yeah.
the correlation plots. Do you have any idea why, for example, the ratio of SPC to GlycB or SPC to GlycA, one's better and one's worse? Or for James, why is there any difference between SPC to But1 or But2 or But3? mean, have any idea why some work better than others, these ratios?
I think one of the reasons why is um sometimes the SPC, like the three OH boot peaks, they vary like relatively more than other peaks. Like they would be like, let's say 30% higher compared to like another peak that's like only 10% higher, right? And also the ratios that I chose, I decided to divide the peaks that went up in the disease cohort by peaks that went down in the disease cohort, so that there is a a more pronounced difference, I guess. So I guess that could also be another reason why some ratios work better than others.
If I may add to this, I believe there is no good answer to that yet. The review, as I recall, doesn't has a good analysis and reference to those research projects which I listed in detail for that matter, and I recommend strongly to look up that review, including the supplementary material, which is extensive, and then refers to all these research projects, which are very diverse, in the same time very coherent in the very much so, because the GlycA-GlyB ratio seems to be very characteristic. In our analysis for the first data set, that was the second close to the GlycB SPC combination. The review doesn't consider the SPC. Again, it was introduced, that analysis part was introduced by the Nicholson group, and for good reason. They have a small handful of additional papers which goes through the analysis of these components and their origin. In fact, they identified some of the phospholipids specifically as well, with a very nice detective work. But I don't think there is a clear explanation why these three peaks, how they relate to each other, making one or the other ratio better looking. In the same time, this GlycA, GlycB plus sum against the SPC seems to be an interesting alternative. And that is the only thing which works at low field, because at 80 megahertz, GlycA, GlycB are not separate. So there is nothing else, just the sum of those two, which you can use against the SPC. The suppression technique does work at 80 megahertz as well, very nicely. So in that case, that's the way to go. Although it would be lovely to check out how Kraft can handle this thing, regardless of the low resolution, because as Chris demonstrated, highly overlapping peaks can be analyzed pretty well. And what Christina showed with Dandy, that is impressive, because Dandy's blood was bright yellow, I can tell. It had so much lipid in there, and it was completely impossible to use it for a conventional multivariate analysis. It had to be completely excluded up front. But the Kraft analysis works perfectly well. So it is still a lot more to do about these ratios, which tells better story than the other, but it is in the process.
Thanks.
Another thing that I want to add a little bit here, which probably not understood or recognized. I literally gave only 1 or 2 hours of my training to this team. That's 1 or 2 hours. My training means maybe 30 minutes of worthwhile information. But they ran the whole thing by themselves. I was providing tech support, if any, by email. So I think we need to really applaud this group of students who just march forward. Whether we are right behind them or not, they just march forward. I think that should be recognized.
And it was a spiritually elevating process as well, I would say. I visited the group every day for a so-called group meeting. They didn't need me too much, and I told them all kinds of anecdotes from my long lifetime. But other than that, they pretty much proceeded on their own. It was fantastic to watch.
It's a good program Princeton has, and I hope to have a yearly conference like this, presenting their whatever the team, whatever they do, not necessarily craft, anything that Princeton Learning Group does, we should have a presentation here.
There is a new cycle of LLP again for this summer. I submitted my proposal and I look forward to the applications.
Yeah. Well done.
So if there are no more questions, and I will say thank you, everyone. This has been a great set of lectures. I really learned a lot from them. And so thank you very much. So I'll conclude the meeting.
Thanks,
Thank
everybody.
you.
Thank you.
It was a pleasure.